Hello everyone, I am Saul Dominguez Garcia. I'm going to talk about this investigation, which is titled Influence of the Spaceholder Addition on the Properties of Titanium, Niobium, and Tin Alloys Fabricated by Powder Metallurgy for Biomedical Applications. The high prevalence of chronic bone diseases among the elderly population increased the demand for advanced materials in biomedical implant manufacturing. Orthopedic implants, particularly those for knee and hip replacement, represent the largest segment in this field. In recent years, titanium, niobium, and tin alloys have received increasing attention due to their favorable mechanical properties and low toxicity. This work aims complementary research to titanium, niobium, and tin intermetallic alloys fabricated by powder metallurgy. Previous research has addressed the study of the microstructure, density, elastic modeling, and corrosion potential of titanium, niobium, and tin alloys for certain percentage of tin within the alloys. However, the current paper examines how the incorporation of spaceholder agent during the sintering step affects the properties of these alloys. The methodology for this investigation includes the following steps. First, pure powder of titanium, niobium, and tin were milled in a high-energy mill to obtain powder alloys, and some samples of the powder alloys were mixed with ammonium carbonate as a spaceholder agent. After that, samples of the powder alloys were compacted and sintered to obtain cylindrical solid samples. These alloys, powder and cylindrical, were characterized by scanning electron microscopy and X-ray diffraction. In parallel, some mechanical properties such as porosity, density, and Young modulus, as well as the corrosion resistance, were tested. The experimental design for this research involved three specimens of titanium, niobium, and tin alloys containing 0, 6, and 12 atomic percent of tin, 30% of niobium, and the balance of titanium for each one. The results of the experiment are presented in the following figures. In figure 2, the mapping of titanium, niobium, and tin, as well as the X-ray patterns on intermetallic alloy surfaces, are presented. In row 8, the micrograph of the powder alloy for 0, 6, and 12 atomic percent of tin are presented. This micrograph reveals a uniform distribution of the elements, and the X-ray patterns indicate the presence of two crystalline phases, a mixture of beta and alpha titanium. In the row B and C, the characterization of the alloys sintered with spaceholder agent and without spaceholder agent are presented. This micrograph indicates some agglomerate of niobium and tin. Also, patterns for these alloys indicate the presence of two crystalline phases, beta and alpha titanium. In figure 3, the mechanical properties of the intermetallic alloys are presented. In graphic A, porosity, in graphic B, density, and in graphic C, the Young's modulus. The calculated values of porosity for the alloys sintered with the spaceholder agent are higher than the values for the alloys sintered without the spaceholder agent. Consequently, density and elastic modulus of this group of alloys is lower than values for the group of alloys sintered without the spaceholder agent. The inclination of the lines between calculated points for the alloys sintered with the spaceholder agent are larger than the inclination of the lines for the alloys sintered with the spaceholder. It suggests that the space-held reagent buffer the sensitivity of the alloys to the sintering process. Figure 4 present the Tafel curves of the intermetallic alloys. In graphic 8 is presented the alloys, the Tafel curves and corrosion parameter for the alloys sintered without the space-held reagent, and in graphic B is presented the Tafel curves and corrosion parameter for the alloys sintered with space-held reagent. From the comparison of this data, the potential corrosion for both groups of alloys present very similar corrosion parameters, and the most notable difference between these two groups of alloys is the variability of the corrosion parameters among the different percentage of tin. Taking in account last results, have the following discussion. The increasing atomic percentage of tin enhances the crystallinity of the powder alloys after the milling. However, the tin content does not significantly affect crystallinity after the sintering process. Micrographs reveal that the incorporation of the space-held reagent during sintering modifies the welding of powder grains, a phenomenon that becomes more pronounced at higher concentration of tin. Porosity of alloys with the space-held reagent obtained higher percentages than alloys without the space-held reagent, except for 12 tin specimens that exchange relative difference. The inclination of the straight lines between porosity points is steeper for samples without the space-held reagent, suggesting that the space-held reagent buffers the sensitivity of the alloys to sintering process. Consequently, density and elastic moduli of the specimens without the space-held reagent are more influenced by tin percentage than the other one. Alloys with the space-held reagent exhibit elastic properties closer to those of human bones. Enhanced porosity and surface roughness could improve cellular responses, as suggested in scientific literature. The corrosion potential of alloys exhibits similar values. However, the most notable difference lies in the variability of the potential and corrosion current density among samples with different tin percentage in specimens without the space-held reagent. This phenomenon can be attributed to the compactible of alloys. Conclusions for this investigation are: in this work, microstructural, mechanical, and corrosion potential of three titanium, niobium, and tin alloys with 0, 6, and 12 atomic percent fabricated by powder metallurgy has been analyzed and compared to study the influence of space-held radiation on the properties. The main conclusions are bulletized below. Space-held radiation buffers welding defects. Space-held radiation buffers the sensibility of the alloys in sintering process and retain their mechanical properties. Space-held radiation reduces elastic modulus of alloys, and space-held radiation does not influence corrosion potential for alloys. Future research should focus on investigating the sintering process of titanium, niobium, and tin alloys produced by powder metallurgy to identify optimal conditions that minimize welding defects and enhance mechanical properties. It is all for now. If you want to know more about this investigation, don't hesitate to contact us. See you later.